All right, recording is now live. Good afternoon, hackers. Today we're going to be talking about binary exploitation. I call it program exploitation. Sometimes it's kind of interchangeable, and reverse engineering. This is going to be the first. We're going to be officially getting into the hacking stuff part of the class, so there will be hands-on demos that you can follow along with. Who here has everyone seen the announcement to set up a Pico CTF account? All right, has anyone not yet set up a Pico CTF account? There will be plenty of yapping in the meantime, so I advise you set one up right now if you want to follow along with how the challenges are going to go. All right, with that, let's get started. What's the plan of the day? First, I'm going to explain to you what kind of ideas are behind binary exploitation, right? Programs, they work, but sometimes you can feed really funny input to make them not work. But in order to determine what kinds of funny input to get them to not work, we got to figure out how programs are laid out in memory and whatnot. Then talk about various techniques for binary exploitation. I mean, I say the word buffer. Actually, who here heard of buffer overflow? All right, you already have step one down. So start with buffer overflows and then talk through various other techniques of binary exploitation. Finally, we're going to talk about reverse engineering, which is essentially binary exploitation, but they don't give you a source code, so you have to start with compiled executables and kind of work backwards from there. Any questions so far about plan, the class, just anything before we get started? All right, let's send it. Okay. What do you need to know before you start exploiting and gain elite hacker skills? Well, ECS50 jump scare. Sorry, it's yeah. We got a quick review of how what happens to the code when you load it into an executable, right? You might remember that C code. You pass it to GCC. It gets compiled, assembled, linked. I forget the fourth step, preprocessor, but that comes first. It runs through all the steps and it becomes an executable, but what happens when that executable is run? Well, you've probably seen some familiar terms here. You see there's a stack, there's a heap, there's some data segments. This is essentially what a program looks like when it's loaded into memory, right? You have your code that's in a segment called text. You have some memory that's in a data segment, and then you have this BSS, gotta remember what it stands for, like base start segment, which is just a bunch of variables that are just initialized to 0, start program. But then after that, you have your stack, your stores all the things as stores a bunch of variables about your program that's running, the function variables, the arguments and whatnot, and then you have the heap where all your mallocs, callocs, and memory issues usually come from. So that's what a program looks like when it's written into memory. Now, a really specific thing we want to focus on today is the stack. Why? Because while your program is running, how does it know where to go next and where did it come from? Well, that information is stored in the stack. I chose not to pull up Butner's presentation, but you might recall from 50 that there's when you call a function, you have to push all the arguments in reverse order to the stack, and then you can call it, and then you have to save all of these registers and things to stack, and then you can put your variables on there. Yeah, still applies. Again, stack stores your local variables for your function are stored in the stack, and I guess quote above that. The diagram is a little, stack, it grows downwards. So you start, they initialize it at the end of your memory, and then as you call more and more functions, it counts in reverse addresses. So diagram, I chose to just move down. Sometimes it goes up, but recall that stack will grow downward as you do more. So higher memory addresses to lower addresses. And of course, your current function is stored between the memory address in your base pointer, and the value of your current stack pointer. Now, of course, once you're done with all your execution, the stack, your program will look at this base pointer address, and then that will determine where it will go to next once you run return. Okay. Anyone have questions about this quick review? Excellent. Okay. So why does all of this stack information matter? Well, program essentially has, the classic definition of computer is it does four things, right? It takes input, it does operations, it reads and writes stuff from memory, and it produces outputs. The purpose of program exploitation is to manipulate the program into doing those instructions beyond what the programmer originally intended, right? What can happen with vulnerable programs is if you give it funny input, you can get it to alter the memory while it's running. This even includes the original code or the stack, control where it goes. And once we have control of the stack, you can do it to, hey, jump to this other function that the programmer never intended to go in the first place. Of course, achieve some desired outputs. That is the purpose of program exploitation. You can summarize it as do what the original programmer didn't intend, but as for pointing out specific things you can do, the ones in bolded are the ones I'd like to emphasize. And relevant TikTok for what the program exploitation, what I like to describe it to people who've never done it before, is this funny one.
This is a square. Can you guess which spot?
Is there no sound? Can I get sound? I think there is sound.
This is a square. Can you guess which spot that goes in?
The square.
That's right. It goes in the square.
Yeah. Audio output. This one. No, this one. Is it this one? Ding, 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 ding. Sound is not working, so I'm just going to blast it from my speakers, and hopefully you will hear.
This is a square. Can you guess which spot that goes in?
The square.
That's right. It goes in the square hole.
Yes. Okay.
And how about this rectangle? That one?
Also the square.
That goes in there too.
Yeah.
Up next, we've got this thin rectangle.
The thin rectangle.
Can you guess where that goes?
The thin rectangle.
That's right. It goes in the square hole. And up next, a cylinder.
The circle.
I think that goes in
the circle.
The square hole. Now, we've also got this semicircle right here. Do you see a slot that would fit
the semicircle?
Semicircle?
The semicircle.
That's right. It's the square hole. Okay. Up next, the triangle. We know what hole that goes into,
triangle.
Right?
Triangle.
That's right. The square hole. And up next, we have the arch.
The arch. The arch.
You guessed it.
The arch.
It goes in the square hole.
Yeah, that is that. Hopefully, that communicates the vibe of what program exploitation is going to kind of feel and look like. All right. I know I've asked a lot about do you have questions? Seems there are none, but can I get a temperature check on how we feel about everything that's been discussed so far?
Check your pickup here. So we just find a bunch of different inputs to a program to try to get the same output.
Not necessarily generate the same outputs, but generate some desired output, like something you want to do. Maybe print some secret value or make it run whatever you want to run. Yeah, thank you for the reminder, Akil. Has everyone been set up with Pico CTF yet? All right, excellent. Let's get started. Okay, so some useful tools you'll need in your toolkit for kind of binary exploitation is first, well, GDB, right? We've used GDB, our best friend in our 36 series classes and whatever classes make you program in C. Yeah, it is pretty much useful in all those gross commands you learned about printing various values and registers. Those are pretty relevant to what we'll be doing today. I will say that GDB on its own is it's fine. You can use it for stuff, but we can do better. There's a tool that I like called Pawn Debugger. It is pretty much, it's an extension of GDB, but you can just download it and run it. It won't affect your original GDB, but what it does, it loads quality of life extensions into GDB to give you a better overview of what's going on, right? For example, in the image, I want to print the stack because I'm doing a stack exploit for something. On GDB, I have to use the, x/80x print 80 hexadecimal values and give it a pointer to whatever value, and it gives me a bunch of stuff that, I mean, I could sit through and read, but honestly, it's painful. Here's me doing the exact same thing on Pawn Debugger. It's pretty useful. It tells me, well, I mean, I compiled this with debug flag, so it just gives you the source code. But hey, look, here's the entire stack. I can see, this is my stack pointer. What's the current value of what I'm looking at with stack pointer? I can look at the whole stack without doing stuff. I can call up registers. It's just a bunch of quality of life things that will make the entire exploit development process much easier than just let me look up a bunch of GDB commands and print a bunch of variables and hopefully I hit the right one. So, I mean, I'll just give it a quick demonstration. I want WSL actually, so that's PowerShell. WSL. Let me just call up an example. Actually, I'll demonstrate it while I'm doing the demos, but actually, if you want to download it, they have some very nice documentation. Good security practices says don't download random scripts from the internet and pipe it directly into your shell and just run untrusted scripts, but I am lazy and I ran it and I don't think my computer's been exploded yet. So keep hoping that they don't get at this, they don't pwn this tool. All right, other tools that will be useful. One is called File. I think it comes default with your Linux, distros, but the other one is called checksec. As kind of name implies, it checks the security of a file. I'll elaborate on that in a bit, but it does not come by default, so you will have to run sudo apt install checksec. I already have it installed, but oh well, I need to update it, so it will look something like this. All right, checksec, and then finally, there is a Python library that will also make developing exploits much easier. It's called Pawn Tools. Pawn Tools, you can install it with pip. I know if you're getting issues about like, your Python installation is system managed, you can't install it with pip. You have to install it through your package manager. I don't know if this will work on this system because it's not system managed, but you can just run like sudo apt install Python 3 Pawn Tools. Sometimes this works. I know when I was running Ubuntu off, dual booting Ubuntu off my system, this is how I got it, but you can also just pip install Pawn Tools, and it's already downloaded. Okay, these are kind of tools that, although not necessary, it will make life very much easier for you when you're doing these kinds of binary exploitation challenges. All right, does anyone need a bit more time to, well, I'm not expecting you to install them immediately, but does anyone need a little more time to look at these before I start exploiting? All right. All right. Let's start demonstrating buffer overflows. You probably already have a good idea of how it works, but let's play some Pico CTF to try and figure out. And I guess this is also a good demonstration to give you an idea of how these challenges work. Challenges will usually involve you getting some kind of flag. That flag is, what you paste in here to kind of say, yes, I solved the challenge. It has the format Pico CTF, left brace, some text, right brace. But you see that, how do I get it? Well, let's just start with the binary and the source. So this one's called heap 0. Actually, yeah. I have the link in the slides, but if you want to search for it manually, it's called heap 0. All right. Let's see. CTF element Pico next. All right. Download the binary and the source. I have already these downloaded. You should get a file called chow and then the source code file chow.c. Actually, I'm gonna open Visual Studio Code right here. Realize I might get an ugly. No, this is fine. All right. Take a look at the C code and see what it can tell us. So binary exploitation, usually get a source code file and an executable you can run. For reverse engineering, they do not give you the source code, just an executable you can run. So start off with what this looks like. Okay. So far seems like it's a decently standard program. I look at main. It runs some. Oh.
It might be okay.
Does anyone see the code fine? Let's like zoom in a little. Purposes. Okay. Looks like there is some kind of win condition I need to do. And okay, you know what? I don't want to look at the source code too closely. Let's just try running it. You might need to give this chmod execute privileges. And I will say that these binaries are Linux binaries, so I don't think you can just run them on Windows as like a .exe. You do need a Linux system to run these. So, shall. Okay. Okay, what does this challenge look like they want us to do? Put my data up on the heap so it should be safe from any tampering. Since this isn't on the stack, I'll let you write whatever you want to the heap. It already mallocs for us. Okay, and you can take a look at heap state, pico, heap state, bico. Okay, what do I do if I want to print the flag? No flag for you. Why does it do that? Well, see, case 1, case 2, case 3, 4, check win condition. What do I need to win? If string comparison, this quote safe variable is not equal to bico, which I believe is the original value. If I manage to change the safe variable, I win. Okay. It looks like I can just write stuff to the buffer. What does the buffer write look like? Well, write to the buffer. Okay. Write buffer, scan F to input data. Okay. Initialize, print the heap, and check safe variable.
Explain what
Well,
the buffer is for this context.
Sure. Buffer in this case is just it's just a variable. It says if you're able to change this, you have some input data, pointer to some input data, you have a pointer to a safe variable, and apparently if you're able to modify the input variable, you win. Okay. Well, the first thing you should always try when buffer overflowing is smash your keyboard. I'm not kidding when do this, write to buffer. Okay, that did something. Let's look at what the heap looks like. Okay, it looks like I absolutely destroyed the variables. Originally it's pico, bico. Looks like I spammed this, and at some point, this get cut off, and this overflowed into bico. So, print flag. Okay, I win. I've demonstrated the exploit. If I just smash the keyboard, it works. But where's the flag? Well, for many CTF challenges, you can test the exploit on your own computer, but in order to actually perform the challenge, you have to spin up what's called a challenge instance, connect to them, run the exploit again to demonstrate that you can do it, and then the flag is on Pico CTF servers, and once you complete the exploit, it'll give it to you. So, launch this instance. It looks like connect with the challenge instance here. There's a command. There's a There's a domain, and then there's a port. Netcat is just a piece of software that just performs a connection over the network. So I think you might need to install it if it's not installed by default, but just run this in the command line. And it's the exact same program, but if I run it here, it will give me the solution. So you know what? Let's write to the buffer. And let's try check safe variable. It's definitely been overwritten, and get the flag. I win. And that's how you get a flag. Right. That's challenge solved. But that kind of begs the question, okay, I just mash my keyboard every time. What exactly about this program made it vulnerable? Right. And before we answer that question, let's just hit up the second challenge, which is very similar, heap 1, heap 0, they're probably in a series. Pretty similar to the first, but it's slightly different. What is exactly different about it? All right. Go, just close this, exit out 1. Open VS Code here. So this looks pretty similar to the past challenge, but if you check the win condition, it's slightly different. This one runs a string comparison with a not. If you remember your function, string comparison, it returns 0 if they're equal, and a true value C is not a 0 value. So it looks like this means that if I'm able to carefully modify safe variable to the exact string pico, I'll win. Just give it a try. In this case, if I mash the keyboard, it might not work. So let's just try writing to the buffer. Looks like, okay, all this keyboard mashing overrode it, but it might not be what I want. So, well, I know that the stuff I mashed in, at some point, there's a certain length that I exceed the original buffer and it starts writing into the safe variable I'm supposed to overwrite, right? So I can just take a look at how many characters do I need to overflow the buffer? I will be using just like this mash to figure it out.
Think you're starting by the D there. One more.
Yeah.
Go back.
DKL. Okay, so whatever is past JLGHW gets written into the variable itself. So I know that if I always enter this string first, then I'll just write pico. All right, let's look at the heap. It looks like it overwrote it, and the string terminated fine, so should pass a check, right? Well, okay, that worked. And just out of curiosity, how long is this original string? How many characters do I need to override before I get to the next variable? Well, just use our old friend Cyberchef. Seems like 32 characters that I need to overwrite before I got to next into the buffer. Why is that? Let's take a look at the code and think about, see if there's anything that says, oh, the buffer is 32 characters long. Well, it doesn't look like they've declared a buffer that's 32 characters long. What is being overwritten? So you write a buffer, I write it into input data. What is input data? Input data is just a pointer. And it looks like they have defined some kind of memory size for that pointer. I assume when they do malloc, just put it. Interesting. They give me 5 characters but it turns out I actually needed 32 to overwrite and write it to the next variable. And this is actually just instance of just system specific behavior. When you call malloc, even if you give it less than 5 characters or less than 5 bytes of data, it will still allocate chunks in 32-bit chunks. I think this has something to do with just like processors, like 32-bit, 64-bit. My computer is 64-bit, but I assume everything is being aligned on, it's 32 bits, 4 bytes at a time. They just automatically give you 32 bits automatically. So good to know. When you're doing stuff, maybe you should start writing in chunks of powers of 2 are pretty important.
32 bits or 32 bytes?
It might be 30. A character is represented by 1 byte. My bad. That is 32 bytes. Thank you for the correction. Okay. But buffer overflows, you can control them. You don't have to mash keyboards, but there is kind of you might have to figure out refinements of, how many characters do I need to overwrite? It's a little hard to just do it by just smashing the keyboard because it doesn't really tell you how many characters you need to overflow. And that's where kind of the tools like Pwn tools and the Pwn debug come into handy. But we'll get into their use in a bit.
But with this case, you must have access for the source code to actually do this kind of thing?
Technically, not really. But looking at the source code allows me to determine, is this vulnerable or is it not? It helps. I mean, reverse engineering, you won't have access to source code and you have to figure it out
That's what
by other means. But
gives you the source code to actually see what's going on.
Yeah.
Like usually you don't have the access for it to begin with.
yeah, sometimes you get them, sometimes you don't. That's why there are 2 categories of challenges.
So we just overrode a variable that should not be written to. Is that the goal?
That's one of the goals. That's one of the goals. I mean, you can overwrite other variables to make the program jump to somewhere else, or you can have it run code that you put in. This is just like the simplest example of a binary exploitation, just doing a buffer overflow and writing into memory you're not supposed to.
Can we explain what happens for like the string comparison?
Sure. Well, I'll use my good friend, the man pages. Man, I will think this works. Aha! Yeah. String comparison function compares 2 strings, string 1 or string 2. If the strings are, quote, equal to each other, if they're the same string, it returns 0. If not, it returns a non-zero value. But the point of this win condition, the string comparison function, is just a shorthand to just say if these 2 are equal, well, I guess I can just, this is logically equivalent to just saying double equals 0, but because in C, a true value is just any value that's not 0. So if you just, not 0 is a not 0 value.
So we overrode it from equal to equal.
Mm-hmm. Yeah. Good. There we go. All right. All right. Any more questions?
How did you know if this is vulnerable to like an entire overflow of buffer? Like what about the source code?
Sure. There are certain vulnerable functions in C that allow a buffer flow. I'll show them off in a bit later. But I mean, on one hand, this is a bit of a contrived example because you're solving a challenge and you know there is some kind of vulnerability in it. But if we look at it, I think, well, first we can just do a check to see how much data am I writing and how much input can I hold. I mean, you'll see that the buffer itself, look at input data size. It's being used in this malloc. Malloc, I believe 5 bytes of data and associated to the pointer input data, and it also did the exact same malloc 5 bytes and associated to the pointer input data. Okay, 5 bytes, but can I put in more than 5 bytes? If you look at the, let's see, input, this initialization. If you just look at the function where you put stuff into the buffer, I think it's what? Hold on, I'm blind. Write buffer. Scanf is using the flag %s. %s is just any string that's terminated by not a new line, but if you just put in a string, it doesn't say, technically it doesn't say how long you could put. I can put 1, 2, 5 characters. And you can see I can definitely put in a lot more than 5 characters. C is very funny in the way that it handles strings because it knows that string has to end with something called a null character. I think it's indicated like what? \0. Can't really type it. But scanf says, oh, I'm just going to read in a string until I hit a null character and just put it into the pointer input data. But the program didn't really say, oh, your data, if you copy more than 5 bytes into the program, this is actually a bad operation. It won't stop you. There's a bit long-winded explanation to say that C is a language that allows you to do things, and that there are certain functions that don't do length checking that allow you to do buffer overflows. Does that make it a little more clear? Cool. Those were the first 2 examples of buffer overflows, but I will note that these take place on the heap. And when most buffer overflows will be, we want control of specifically the stack. Heap is your malloc memory. Stack is where your variables are, but also where you store, where do I jump next in the program?
Is the because you were writing into that burst variable, right? How did you know did you know that it was gonna overflow into the other one because it was allocated after, or was that what you were using to determine that?
Yeah, that's probably good to know.
Input data first. And then, save variable, right?
Sure. Actually, let me run back to I believe this. The fact that they're just next to each other in the heap. Oh yeah, the fact that they are called malloc right next to each other, so they are assigned adjacent portions of memory. So that does help to be like, hey, I can probably overflow this.
I mean, but if you swap them, for example, would it not work? I suppose you.
You know what? Let's give it a try. I'm curious here. Let's see. So in this input data malloc, so actually can actually give it a try. Yeah. Modified called for input data. Let's compile it. Let's see. I think I can just compile it without any. I'll just use a.out as a.out. Let's give it a try. See that they are. Oh, that's really funny. These end up being the exact same address on the memory. If I look at just normal challenge binary, 6B, 6D. Okay, interesting. If I do change it and compile it myself, it has different addresses. You know what? This is a good time to demonstrate check security. Let's see what kind of security protections I have on both binaries. The one that I got that says no, it's vulnerable, and the one I compiled by myself. Sec and check sec. Okay, check sec. I just know that file. Let's see. Shell. Okay, interesting. File a.out. Okay. In order to demonstrate that challenge, I'm gonna have to disable these compiler features. I'll give it a try after class, but I'll keep that question in mind and remind me at the end of class. Because I think you might see that some of the protections, operating system protections, have messed with what the challenge has been able to accomplish. Because you see that, oh, heap, these 2 addresses are different, and they're next to each other. Actually, if you do like the binary math, you'll tell that these addresses are 0 hex 20 apart, which if you do the hex conversion, actually converts to 32 apart. So fill
Sure.
32.
So they're like adjacent, right?
Yeah,
But
they
is
were
it-
adjacent.
Wait, are they like? Which one was the safe variable now? Because you're like swapping. or-
Let's see. I believe Pico is the safe one, and Pico is the Pico is the unsafe one. Pico is the one you can mess with. So if I just run print heap, write to buffer test. Yeah, that first one, the B0 is the one you can mess around with. D0 is the one that's supposed to be written and is at a lower address, so kind of extends off the end. I don't know if I can. Yeah. A little messy to demonstrate, but have 32 bits. Let's see. Pico. I should write larger, but
Yeah, so
I'll
that's how I
just
did it
gesture
over
as it, and then it just goes up. That's essentially what overflowed. I will say that the compiler protections for the one I just compiled, so .a.out, you see that these.
Yeah, but so now like the Pico is the one that you can actually mess with, right? So it's after now, right?
Yeah, it's
So it
after
only
now.
works if it's mallocated before the other one, right?
I swear I saw the addresses were the same earlier. I don't know. Yeah, let's give it a try.
None.
So let's see, Mogus. Or actually, I should spam the keyboard. So, and if I check the buffer, no, check the heap. Let me just give it a little more extra just to be certain.
But no, it is after, right? So
Yes, it is technically logically after, but just to be certain. Yeah. So just because the order they were allocated means that you can use Pico to overwrite Bico, but that's specifically just for heap because heap grows from lower addresses to higher addresses. Stack is a little different, as we'll see. Okay.
What challenge is that?
This would be heap 0 and heap 1. Okay. Any questions so far about what's been discussed? All right. Okay. Now, here's a different challenge. We were talking about the heap earlier, but what about the stack? We know that the program stores information about where it's coming from, where it's going, its variables, arguments, and whatnot on the stack itself. If we have control of a local variable on the stack, and that stack is vulnerable to buffer overflow, what can we do with that control? And for that, I will raise this challenge. This Echo Escape 1. There's a secure Echo service that welcomes you politely, but what if you don't stay polite? Okay, let's pull it up and take a look. No. Echo Escape 1. All right, pull up the source code and see what this does. Okay. We can see, okay, starting off, we can see obviously there's a win function that we need to target, that we need to run. And there is a main function that just runs and assumes that it just prints stuff, reads stuff from the input, and prints the output. Fine. Very funny thing though. Can anyone see where the win function is called in main? Yeah, I don't really see it either. So the win function is never called in main, which means I can't get to it. So it means this challenge is unsolvable, which means I can't. Oh, what do you mean 1,870 people solved it? Okay, so there is a way of getting to win without win ever being called. And we know that stuff on the stack controls what kind of functions you can jump to. So say if we had a control of a variable on a stack and then we use it to overwrite stuff on the stack, maybe we could use it to jump to win. Oh, would you look at that? There's a buffer variable that gets read into. All right. I'm just going to spin up the challenge instance just to show off, take a look at what it does. But in the meantime, let's just run the provided binary vuln and see what it does. Okay, enter the secure echo service, enter your name. Jason. Hello, Jason. Thanks for using our service. Okay, so it looks like they're okay. Flush standard output. I read some stuff. Let's see. Read. Very interesting.
What if you give it more than 128?
Exactly. You know what? Let's read the documentation and see what read does. Read function vulnerabilities. Oh. Looks like someone's asked this question already. Can the read function leave to overflow? If a size and array is 100 and I read 100, is there an overflow? Read and write with buffers. Let's see. Believe what read does, it takes returns stuff from buffer into the file descriptor. I believe guessing at is probably, oh, let me take some standard input and then put it into the buffer, and it always reads 128 bytes. Okay. Oh, this is very interesting. The buffer is only 32 bytes long. So what if I just kept writing? At this point, this is where I call up my good friend Pond Debugger to show what is going on. Oh, I need to. Do I not have it installed? Give me a second. Well, demonstrate the installation process. Good security practices, I swear. In the meantime, let's just pop it open with GDB and see what we can figure out from where. Hi. Oh, this is command prompt. I just opened command prompt again. What am I doing? Okay. No. Yes. We go in 1. GDB. Oh, I just hit tab and it's going to not like me for using tab. Okay. No debugging symbols found in vuln. That really sucks because I want to, like, I see the source code. I want to break before and after I read input. Can I just say, so I don't have any debugging symbols. What if I just compiled the program and gave myself debugging symbols? Well, fortunately, I have already done that. There's a version I compiled the code with, and I added the -G flag, and I can just do vuln debug. Yeah. Vuln debug. Excellent. Say I want to break at line, say break at line 30 after I read input. Okay. And I want to know if I need to jump to the address of, if I need to jump to the win function, I probably want to know where in memory that is. So you know what? Let's call up function info address. Argument required info address win. Say function at address 0x401256. Okay, where are we right now? Main. Okay, that is a different place. Okay. You know what? Let's just start applying lots of buffer overflows and see what happens. Okay, I'm paused, and you know what? Let's start checking the stack. Well, info registers. Yeah, I could. Info buff. See, this is why I don't use GDB. It's usable. You can get some basic information out of it, but there's still, I would very much have the ease of use for pond debug. Let's try it with pond debug instead. Pond debug. Okay. Let me set a breakpoint at 30. Let's just run it. Test. Whoa, this is a lot of information that probably useful for me. Let's see. Shows me the values of all my registers. That's pretty cool. Shows me the exact assembly code of what I'm currently running, and shows me, okay, the source code that I have. You get this with GDB anyway, but it's good to just look at it immediately and not have to call for it. And oh, would you look at that? That is our stack. Looks like there's some information in buff. And if you remember, the presentation of where is the return address? It is right above the whatever EBP is. If I look at, well, it's not, well, for X 64-bit, it's RBP, and oh, look at it. It goes to, once I'm done, I return to this address, and it looks like it goes to a function called libc start call main. What if I went somewhere else? Let's run this program again, and let's just spam A and see what happens. Oh, that's pretty good. I've overflowed the buffer, and looks like, ooh, this is, looks like I've overwritten a little too much. So what do I do from here? Well, first problem is I'm just spamming A. I'm not very fast at counting, but, well, I don't know who's very fast at counting, but I can say that just from looking at this, I can't tell how many A's I need to exactly reach the return address, the 8 above the base pointer. So let me use something else. Let me just spam something that maybe has, I don't know, a pattern. I mean, pattern number's nice, but 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Count by tens. That could work. Or 129, 129, 129. There is. That is also true. I'll say there is a very specific tool that will speed up how you find how many you need. I'll just call it cyclic pattern. CTF. Let's see. Website. There's a very nice buffer overflow pattern generator. This is pretty good. What this does is it does all the conversions for you. I generate a pattern, I put in some text, but I don't need to manually count or like start string matching to figure out how many characters do I need. I can just say, oh, put in whatever is in the memory that you want to look at, and then it'll tell you automatically what is the offset from your buffer to that target area of memory. So let me just say 50 for now. Automate it. Let me just run it again. Okay, and I know that this area of memory that I want to target has been overflowed with this, So if I, bruh, 50, let me, so 0 hex offset. Do I get an offset? No, I do not get an offset. See. Sometimes a little finicky, you have to format the data a bit.
You can take the B3 from there.
Say again?
Can you take it from the B3?
Yeah, technically B3. So let me just count. Yeah, so I'll just do it by hand then. What's the character count? So if I know that. Okay, this is 50 characters. So I know there's an offset of, oh wait, no, that's a little too much. Yeah, so let me just go here. 40 characters. 40 characters to overflow the buffer and get to that critical return address that I want to overwrite. And I know that the address I want to get to, actually, just info address win, and I want to replace whatever was in that return address, so this memory, with 0hex 401256. Okay. Then 401256. Okay, you know what? I can just convert that to ASCII and see what happens. Make a div bit. What is 40? You know, as you can see, if you remember that the characters are not directly represented in memory by like 1, 2, 3, 4, 5, they're represented in ASCII format. A, for example, is like 41, 0hex 41, and so whatnot. So I need to figure out, and this is reading strings, so I need to figure out what characters can I type to get this, essentially. Okay. Okay, I want to convert this. Let's see, from hex to character. Ooh, those are okay. I can type 2 of those characters, but this does not look like something I can type. You know what? Google how to type in terminal. Oh, it's a non-printing character, so I can't actually type it. Let's see, what was the hex address? How to type in terminal 0hex 12. Ah, interesting. This is the reason why Control V does not work in terminals. If you just type Control V, it is kind of a special sequence for you to type characters that are not typically typable. You have to hit Control Shift V to actually paste. So in order to type this 0hex 12 decimal or ASCII, you have to do Control V and then Control R. Interesting. Okay, let's give it a try. Run. I want this entire 40 character sequence. And I want, what was the characters again? At, and then that non-typable character, Control V, Control R. Oh, G. I realized I was doing this on Ubuntu, so it might be a little different on Windows. Type in terminal 0hex 12 Windows. I think there was a alt code. Alt 018. Okay. Alt 018.
No.
Yeah. Actually, if I just do this, oh, Control C, exit it out. Let's see. Run it again. Paste this. And I want to type, let's see, 0hex 12 ensure numlock is on. I don't even know if I have that on keyboard. Okay, so there's a bit of a problem. There's an untypable character that I can't. If I try and just type, let's just like at 0hex 12 v, and I just run it, it transforms those characters I typed. It doesn't treat it as like a literal hex value. It transforms it as the characters 0x12, and if I just continue running it, seems like nothing really happens. So this is where something like pwn tools, that Python library, comes in. So I have already crafted, say, go.
As your terminal settings, you can disable it.
Yeah. Okay. So in the meantime, let's just write it up in Python. I already have like a strategy developed, but essentially, you know that you have a buffer overflow. You know that you need to spam 40 characters in. and then you have a payload, which is the address that you want to go to. So you know what? Let's just start typing it up. Let's see, chow equals process, open the process, boom. And then I want to read and I want to send it input. So let's see, chow dot, wonder if I send, well, let's just build up the payload. Payload equals, let's just say A 40 times plus the, let's see if I remember how to do this correctly, 0 hex backslash, sorry, I'm gonna have to figure out a Python reference for this. Python insert bytes. This is not exactly what I wanted. Python send literal bytes, which use hex 12401256. I'm just gonna use Gemini for this. Data equals this literal, and then boom. Okay. Child.send payload, and then child.receive all. So this is essentially what Pwn Tools is just like, I don't know if anyone's heard of like a tool assisted speed run on like video games before, but what it does, it just mimics the inputs. You define a specific input you want to give to a program. It'll kind of play those inputs and then you tell it to receive data. And then using those commands, you can very finely control the data you want to send and receive from a program in order to accomplish the exploit. No. Py. Okay, can only concatenate string, not bytes to string. Let's see. This is let's see. What about dot encode? Don't know if this is valid Python, but I'm just play by ear. Okay, it does not have encode. Give me a second. Let me see if I can find the original code I had for solving this. Oh. Okay. Build up the payload. I want to send, let's see. Well, if I don't know how to use Pwn Tools, I'll use the ever so helpful Pwn Tools docs. And there is a very useful there's a very useful GitHub that just gives you a bunch of examples that I can use with. This is not the tutorial. Pwn Tools, and I want tubes. How do I send data to this? These are all the good functions I want to use. Receive, next line, pattern, okay, just want to send stuff to it. Well, most of this is just type errors. Concatenate, well, screw it. Concatenate bytes with string Pwn Tools. Or actually, can I just encode this as bytes? Python is very specific about types, so I gotta be careful with Python solver.py. Huh. Okay, it ran something and then it exploded. It's not a good sign. Let's see what happened here. Let's go back. Let's just go back to originally using the Pwn debug and just figure out how to type that 0 hex 12. So I know that I can type. Actually, if I can just copy paste this. See if this works. Yoink. Run. Paste this, and then paste this. Well, it didn't print, but see what got written into the base pointer. 0456. Ooh, 56. And you'll note that because it is the endianness of the data, it's written backwards. 0408. I didn't write the funky hidden character. Let's see. Let's go back. Type 12 in Windows terminal.
Which one does terminal, or is it WSL?
That's true. Windows terminal WSL. Type DC2 character. R. Oh. Run. Control R. Zero. Control this. 0 hex. At. Control. C. R. No. At. Control V. Bruh. No. Controls are possible to make this work. 0 hex 12. Actually, I think I know what's missing from this. This program requires that there be a character called flag.txt, and it prints that when it runs. I don't have flag.txt in here, so you know what? Let's make flag.txt. You got the flag. Let's try running it here. Retrieve the data. It's still segmentation faulted. Okay. I do not want to give up on this challenge, but I realize there's an entire segment of the lecture I have not covered. So in the meantime, I will speed run this. Sorry? Next Tuesday? Okay, I'll have it figured out on Windows. I swear it worked on Linux. If only I wasn't using Windows, guys. Propaganda. Okay. What can we do to avoid buffer overflows? Well, first things first is there are certain functions that don't do type checking when you do a buffer overflow. You might have heard one called like gets C function. Gets, it reads a function, stores it, but it does not do type checking. Not type checking, does not do length checking. It runs. If you put in a longer string, it will blow up your buffers. So, I mean, you could do that, but sometimes there are plenty of buffer overflows that go on without using quote bad functions. Actually, let me just pull up a few examples I had in my notes. I think this one. These two. This is actually an example of a buffer overflow in, if you would believe it, Java. Use a Java overflow, and all they did was just, if length less than 0, throw an out of bounds exception, but that wasn't enough they're not using an unsafe function like gets or puts or name a random C function here. All they did was just, we didn't put enough checks in the length check before we threw an exception. So I mean, yeah, buffer, if you just don't use unsafe functions, you could stop buffer overflows, but that's not going to stop all of them. Another solution people propose is just don't use C. As you can see, there's a very common thread with all the examples I'm using, and it's called I'm using C. All the people who are using Rust, Ethan especially, are going to be yelling at me, if you just use Rust, you would fix all the security vulnerabilities tomorrow. And yeah, I mean, Rust and other languages like Python and whatnot, they do protect you. If you're trying to access index, like, if you declare an array of size 4 and you access something 5, it'll throw an error at you and say, hey, this isn't right. it will stop you from like blowing up corrupting random memory. But a thing with buffer overflows and these other types of binary exploitations, we know these specific challenges are really designed to like, oh, read some memory and get a flag. But if you go and look at the list of security vulnerabilities discovered and sort by buffer overflows, most of them are not just about, oh, someone was able to do some super hack and get into 500 computers with it. It could be something just as simple as I made the program crash. And in security, making a program crash sometimes is just as bad as it having a really gaping bug. So programmers can't always avoid buffer overflows. What can we do then? Well, what if we just made the operating system protect you against buffer overflows? And that is the function purpose of a thing called a stack canary. When you run a program between, this very important return address and your more variables. What if I just insert a random piece of data and check if that gets touched, crash the program because someone's trying to touch your program? Sure, that definitely works. Of course, you'll see that I'm able to do a lot with these challenges. Actually, if you run, just exit, check sec vuln -- file equals vuln. You check that these programs are actually compiled with no canary to make them deliberately vulnerable, but most programs today are compiled to include a canary that will explode if you try and mess around with it. I will touch. Okay. Let's see. I'm going to skip straight to reverse engineering, and I'm going to jump back to the other vulnerabilities just in the interest of time. But talk about reverse engineering. Mostly the same thing about binary exploitation, except source code is not provided. Extra challenge of reverse engineering is that when you compile a piece of code, all your variable names and function names and all the things that make code readable, it goes out the window. It's just a bunch of C-looking code, but you can barely tell what's going on with it. You know what? I will give you an example. Different tools you can use for it. A decompiler and a disassembler are technically two different things, but they're usually bundled together because it makes life a lot easier. Essentially, when you compile code down to it's like machine code, go from like code to assembly to machine code, you use a disassembler to convert that machine code, those zeros and ones, into assembly instructions, and then people figured out that, wow, GCC really likes producing the same predictable thing every time for the same code. What a surprise. So they're going to say, oh, we've seen these assembly instructions, they map to this printf function, or they map to main, or a lot of common functions. So the compilers take the extra step of taking that executable from assembly to, you know what, let's give it a stab and try and make something that looks like C code out of it. Two I really like to use is, one is called Dogbolt, which is a website that does it for you, but it only handles like small projects, which is good enough for homework and CTF challenges. And one developed by the NSA called Ghidra, which is a full-on, very involved, gives you all the code, and you can slowly pick at it and rename variables and be like, oh, this variable is actually virus or counter or whatnot. Just demonstrate its use real quick. Dogbolt. Think that's not what it is. Dogbolt. Decompiler. .org, not .com. They're cool like that. Okay. Let's just upload the exact same executable I've done. Let's see. This will try and generate source code from an executable when it's normally not provided. Go. Linux. Let's just use the echo escape that we all love and been trying to work at. Okay. And you can see they use a lot of different decompilers in this. Some of these are paid products, Binary Ninja. See, Ghidra is not paid. I don't know how many of these are paid, but essentially this is just a free service offered by a bunch of nice decompilers to just run it and try and give you something, even though the actual projects are just like something for hobby projects you don't need. Okay. As you can see, this is a whole lot different than this. This is very nice original source code. This is a whole lot of random stuff. See that they've included a lot of what seems like C function. Oh, there's read, there's close. This is like puts, which is related to printf. And I'm just going to limit it to these two just for convenience. Do you see that some function names are preserved? That's because when you compile it, they will include some symbols just for simplicity, but you can choose to be like, oh no, I don't want to help anyone with the executable. I want to use as little symbols as possible. So win still gives you a lot of similar things, but as you can see, all the variables are unnamed. So I think this was originally, okay, this is just a character buffer. This tells you, actually, everyone can see the screen fine, correct? Okay, yeah, does not tell you anything about the variable type. I can say, oh, this is an array of 128 characters. Oh, here's a file pointer that gets passed to when you do fopen. Here's some strings. And half the challenge is essentially just looking at the code and figuring out what the original thing could be.
What if functions does such a thing to another and make it a little bit more readable in this case?
Sorry, say it again.
Giving this to like an LLM, wouldn't it make it be more readable?
Honestly, I haven't tried. That could be something you can experiment with.
Like ask it to rename the variables for something more reasonable.
Yeah, just like trying to figure out what kind of variables does it look like. Yeah, that could be a very good application. Just for demonstration purposes, I will compile the Vuln program with, GCC-C without C, and then with a special option -S that removes a lot of the symbols. So, C-G vuln.c out vuln debug. I think, yeah, this is fine. So it just compiles it into debug mode. Let's see how different this looks. Oh, this looks like it's taking a while. So I'm just gonna duplicate it and compile with an extra option called -S. So stands for, I believe, stripped. So it just removes a bunch of the helpful. It will remove even function names, so you don't get to see something like win. See that this is taking a while, but win character buffer looks like, and this has provided a lot more helpful data. This is a register, but still looks like they've taken out. They've kept some of the variable names. They've put buffer back in. I believe this is just 128. That's pretty cool. Then let's look at, yes, the stripped down version. See what information this gives. Start. There's a main function, but this, you can probably tell with like the file open, this used to be the win function, but this information, they don't even give it. At the bare minimum, when you do reverse engineering, you should be able to at least tell, they will at least tell you where the main function is, because every program starts with main function. But in the very worst case, you will have to figure out everything for yourself. In the best case, they provide you some extra data that's bundled in that will tell you what the original code was. Okay, we're approaching max time, but all right. Thank you, everyone. Any last questions before we go? C compiler. Recompile. I mean, it was just compiling. Check if the addresses. If you move the order, the answer your question.
Yeah.
Cool. All right. Thank you very much. Stop the recording.